Hello. We will be talking about calorimetry today. Calorimetry is how you measure the amount of energy in a substance. So, as you may or may not know, energy is contained within chemical bonds. This is a type of potential energy. So for example, if we have a compound with carbons and hydrogens, we've got carbons, just to review our Lewis structures a little bit. There are two different types of bonds in this molecule. There's CH bonds and there's CC bonds. And then if we combust this, so we undergo combustion, which is reaction with oxygen, and this is what happens when something burns. So this is ethane, for example, which is actually a fuel, and you can burn it in oxygen. And the products are carbon dioxide and water. Okay? And just to make sure that everything is balanced properly here, we have to adjust things a little bit here, so we actually need two of these. So I'm just drawing this all out because I want to make sure all of the bonds are accounted for when we talk about our calorimetry. So we'll have two of those, two of these. Sorry, 1, 2, 3, 4. We need 4 of these. It's a little easier to balance equations when you have the formulas, right? But C2H4O2, okay. So then our total number of hydrogens here is now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that means we need 6 of these. So maybe I did this wrong. No, that's right, okay. So 6 waters. Okay, I think that's all balanced. So our total number of oxygens that we have to add over here now is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 oxygens. So we need 7 of these. There we go. All right, so that's the full combustion of ethane if we actually drew out every single molecule. And the reason we want to do that is because we want to account for the types of bonds and the numbers of them. So over on the left side, instead of our normal balancing, we're going to count up types of bonds. So in this side we have 2 carbon-carbon bonds. We have 12 carbon-hydrogen bonds. And we have 7 oxygen-oxygen double bonds. So just a different way of counting them. Okay, and then over on this side, in our products, we have, let's see, we have 8 carbon-oxygen double bonds. And then we have 12 oxygen-hydrogen single bonds. I think I got everything. Let me know if I missed something there. So sorry I'm covering this up a little bit, but it doesn't really matter. Okay, so now we can think about what's actually happening in this reaction. So as I said, ethane is a type of a fuel. It's a hydrocarbon, much like gasoline or something like that, just smaller. And so if we set it on fire, we know what happens. It burns, right? And if it burns, it's giving off heat. So if it's giving off heat, that means that there's some heat in the products. We don't draw them because heat doesn't have mass. We don't draw it as part of the equation, but we know that there is some heat coming off as a result of this reaction. Some reactions suck in heat, those are called endothermic, and some reactions give off heat, which is called exothermic. So what this tells us about the bonds here is that these bonds that we started with are higher in energy overall. They have more potential energy than the ones that we ended with, because if we started with these and we went over and made these, and there was leftover heat, leftover energy, that means there was more energy over here between these and less energy in those, because the rest of it came out here. So we're conserving energy by releasing the rest of the energy as heat. And it's actually quite a big difference. And this is one reason why hydrocarbons make such good fuel, is they store up all this energy in these carbon and hydrogen bonds, which they can then get rid of when those bonds are converted to the more stable carbon-oxygen double bonds and hydrogen-oxygen single bonds. It's another reason why, as we'll talk about in the next, or in 2 units, why global warming is such a difficult problem. One of the reasons why global warming, global climate change is such a difficult problem is because of this energy imbalance. Burning these hydrocarbons releases a lot of energy. All right, so back to our question originally, which was calorimetry. How do we actually measure this thing? So for those of you who did lab already, you kind of have a sense of what we're going to do here. But we didn't really go through it carefully, so let's do that now. So 1 calorie is a unit of energy, and it's defined as the amount of energy it takes to raise 1 gram of water 1 degree C. So you have 1 gram of water, which is also 1 milliliter, and you want it to go from, let's say, 22 degrees or so, whatever room temperature is right now, to 23 degrees. So it takes 1 calorie of energy to do that. That's how that unit is defined. We have to be a little bit careful when we convert this to other things that we know about, and when we talk about macronutrients, we'll get into this a little bit more. But in the US, when we talk about food, this is actually not the same unit that we're talking about, even though that one is also called a calorie. That is a capital C calorie, and it's actually 1,000 little c calories. The abbreviation is CAL for calorie. That's really confusing because even though I exaggerated it a lot here, as you know, C's, capital C, lowercase c, it's basically the same shape. So if you make your C too big or too small, all of a sudden you're off by a factor of 1,000. So that's why in most other places in the world, they refer to that as a kilocalorie or a kcal. So when you see calories listed on a food label, those are capital C calories, which are actually kilocalories for the measurement that we're going to be talking about when we talk about calorimetry. When we talk about calories, measuring calories in the lab, we're always talking about this lower C calorie. All right. So if a calorie is the amount of energy it takes to raise 1 gram of water 1 degree C, that actually gives us a really convenient way of measuring how much energy something gives off. If something gives off energy, and then that energy is used to heat up some water, we can measure the starting temperature and the ending temperature of the water and actually figure out how much energy it took to make that change. So the basic calorimetry calculation or calorimetry experiment is we're going to combust something and use that energy to heat water. So in our example earlier, if we wanted to know how much heat came out from doing this reaction, we could take a known amount of ethane that we measured. It's a gas, it would be a little tricky, but we could do it. A known amount of ethane, we burn it, we get all that heat to go into some water, and then we figure out what the change in temperature of the water is, and then we just have to multiply. So let me show you what this equation looks like. And it always uses some variables. I'm going to use them here just because we're going to use them later when we talk about our calculations for the biodiesel experiment tomorrow. So I'll define all this stuff. Q equals m times c times delta T. We've actually talked about pretty much all of these terms already, so let's define them. Q is heat. That's a little bit confusing maybe, but heat is not exactly the same as energy. And H is already used for some other stuff, as is letters that mean heat in other languages, so it ends up being Q. M is the mass of water. So how much water are you heating up? C is the heat capacity of water. So when you heat up the water, how much energy does it take to raise it 1 degree? If we're working in calories, we can pretty much ignore this term because the heat capacity of water is 1 calorie per gram degrees Celsius, which that looks like a really complicated unit, but it's just saying what we wrote up here. A calorie, 1 calorie raises 1 gram of water 1 degree C. And so that's why that number is 1. If we were heating up another substance like our calorimeters, metal, things like that, that heat capacity would be different. Okay, and then the final term is delta T, which is the change in temperature. So it's not the absolute temperature, but it's how much did the temperature change from beginning to end. So that might be expressed as the final temperature versus, or minus the initial temperature. Okay, so this might be most helpful, or most, it might make more sense if we look at an actual example of doing this, especially for those of you who haven't done this in lab yet. All right, so we're going to put a sample in a calorimeter. We'll just call this box a calorimeter. And we'll put our sample in there, whatever it is. Okay, and then we're going to submerge that in water, right? Because we want all of the energy to go out into the water. All right, so let's say we have 4,000 milliliters of water, which would be 4,000 grams of water. And we put our calorimeter down into the water, which is just a container that our stuff is going to burn in. We have to add oxygen so that it burns, so we like pump a bunch of oxygen into it first, put it down in the water, and we take our initial temperature. Let's say our initial temperature of the water is 24.6 degrees C. And then we start the reaction. So the way we will do that in lab is we'll connect electrodes down into the calorimeter so that we can produce or heat up a filament and start that combustion inside the reactor, inside the calorimeter. The stuff all burns, and it starts emitting its heat to the surroundings. But the surroundings are all this water. So we can measure how much the water temperature is changing as this happens, and eventually it will get to some high amount, and then it'll start going down again. And usually we don't want to have a huge amount of change here. So our final temperature in the water, let's say, is 25.8 degrees C. So we started at 24.6, we did the combustion. You know, we haven't talked about the amount yet, but there's however much fuel in there. And it's heated up the water to this much. So now let's use this equation to calculate the heat that was produced. So the heat that was produced, Q, is equal to the mass of water, which is 4,000 grams, times the heat capacity of the calorimeter, which is 1 calorie per gram degree C, times the change in temperature. So the change in temperature is going to be the final temperature minus the initial temperature, which in this example is 1.2 degrees C. All right, so that's our calculation for the heat produced in this particular process. And that equals, in this case, this would be 4,000 times 0.2 would be 800, so 4,800. And that's little c calories. So that's the amount of energy that was produced in this process. And we know that because we were able to monitor the starting and ending temperature. We knew how much water was being heated up, and we measured how much it was getting heated up from the starting to the ending temperature. Okay, so that's a basic calorimetry experiment. That is fine, except we didn't talk about how much actual sample we were analyzing here, how much ethane. Depending on how much we put in there, that's going to affect the final temperature by a lot, potentially. If we put less ethane in there next time, then we're going to have less of a temperature change. If we put more in there, we're going to have more of a temperature change, because the more stuff that burns, the hotter it's going to get. So we have to have a way of standardizing these measurements so that we know, well, how many calories does ethane actually have per a certain amount, not just how many calories came out of it in this particular experiment or this time. And the measurement that we use for that is something called energy density. Which for us is going to be calories per gram. Now there's lots of other ways of measuring energy besides calories. There's joules, there's BTUs, there's kilowatt hours, there's other ones that I'm not thinking of right now. Lots of ways of measuring energy. We're using calories per gram, but we could always do some conversion if we needed to use a different unit system. So our energy density is calories per gram. That way, let's say we used, let's say in this previous experiment here, that we used 0.5 grams of sample, half a gram of sample. So then our energy density is calories per gram, so 4,800 calories per 0.5 grams is 9,600 calories per gram. So this tells us that every gram of ethane should give off 9,600 calories. That's what that's saying. So even if we use more, like let's say we use a whole gram instead of half a gram in the next experiment, we would expect to get double the amount of calories out. And so then when we did the division, we should end up with 9,600 again. Now, of course, it's an experiment, so it's not going to be perfectly the same every single time, but that should give us a general idea. Oh, lights went out. Hold on, I got to dance around to turn it back on again. All right. So that's how a calorimetry experiment works. Now, a couple complicating things for when we actually do the calculations from lab tomorrow. Same time, by the way, 1 o'clock. You may have noticed this, maybe not, but actually not 100% of the heat went into the water in this case. A lot of it went into the calorimeter itself. For those of you who did the experiment on Monday, you remember that those things are big, heavy hunks of steel. So a lot of that energy actually goes into heating up the metal itself and not into the water. So when we do the real calculation for the biodiesel, we have to take that into account, and we have to add an additional term for the calorimeter. We have to know how much energy went to heating the calorimeter, and then we have to add that to the amount that went to heating the water. So we'll get into that tomorrow when we go through the actual numbers, but this is the basics of just what calorimetry is and how it works. You don't have to use a fancy calorimeter for this. This is something that you can measure with just lighting something on fire and having it heat up some water. It's not going to be as precise as if it was actually fully submerged in there, but you can get some readings that way. There's also calorimetry that doesn't involve burning. If you're just like measuring how much energy is in some ice, you can melt it in water in a styrofoam cup and measure the temperature difference there. There's various things you can do. If this kind of analysis is something that interests you, that might be something you propose for a final project, and you can use whatever we have that you need for that. All right, well, that's calorimetry. Hope that made some sense to you, and we'll work with the actual numbers from the experiment tomorrow after all of the groups have collected their data. See you later. Bye.